definitely have to turn it on first. Thank you everyone. I think I'm noticing like an inverse squared law. The likelihood of sampling an audience member increases the further away you get from the stage. So it's okay, as long as you can all hear me. My name is Jawad. I'm part of Borealis AI. I have Wasim here with me as well from Borealis AI. How many of you know who Borealis AI is? Show of hands. Okay, the two people I've been emailing. All right, that's how many of you know RBC? Okay, a few more hands. All right. Well, I hope one of the things you'll walk away with today is you'll be able to raise your hand if this question were asked again, if I've done my job well. So one of the things over the course of the next 30 minutes, what Wasim and I hope to accomplish here is to give you a sense of who we are, what our machine learning workflows look like, and what is the context and the environment within which we do that machine learning. And hopefully that will set up a context for what are the challenges that we faced and how we were able to use ClickHouse and the surrounding ecosystem to mitigate those challenges to some extent. Who we are, ML workflows, challenges, our ClickHouse ecosystem. So, Borealis AI started off in 2017 as this ragtag team of academics and one engineer back in 2017. And what we hoped to accomplish was to bring this as yet nascent field of machine learning. Machine learning had already come out of its winter rest. It had made many promising advances in academia, but as yet much was left wanting in industry. And our founder, Fathini, she set out to establish this research and development arm within RBC to show that machine learning had a lot of transformational promise for financial applications. And as you can imagine, a bank being a bank, it had superb infrastructure and platforms for what has now come to be known as OLTP, online transaction processing, right? Which is storing and computing transactions at a very large scale. But we were woefully unprepared for the type of analysis that we need for machine learning, which is OLAP, especially in the data exploration and feature engineering stages, yes? Which involves a lot of aggregation, a lot of finding different views to build an intuition of the data we're looking at, often at very large scale. And so over the past decade, one of the things that Borealis has done has been to, and hopefully you'll see one of the examples of the stories that we're going to be presenting today is how we've been able to bolster the OLAP infrastructure at the bank. And so today Borealis is an end-to-end machine learning delivery group at RBC. I promise I'm not here to sell you any financial products, although if you do want a job. RBC is Canada's largest bank by market cap, over 80,000 people worldwide, and we have a very diverse team. We have to have a very diverse team because, being a bank, very, very different types of business domains. And so, as we will see later in the machine learning workflows, a big chunk of our work is actually trying to develop intuition about what data each business domain has and what kind of an architecture and what kind of algorithms might help them. So just to give you an idea of the type of environment we have at Borealis, a bank is a regulated industry. So our machine learning workflows are designed to be committed to responsible data practices. Although we are looking at a hybrid compute strategy, we are predominantly on-premise. That leads to a lot less friction about where data is stored, and we already have a very vast regulatory infrastructure, governance infrastructure on-premise. We're in the process of figuring out what happens in the cloud. Large scale, right? Just banking transactions, over 40 million transactions a day, and many, many business domains. So this should look pretty familiar, yeah? It's pretty standard in industry today, this process. But two of the things I would like to draw your attention to is the scope and the feature engineering. So just because we are very diverse, it's very difficult to generalize one solution to another. Personal and commercial banking is not the same as capital markets. They have completely different systems, completely different business objectives, and completely different personalities. And in the scope section, a large part of our work is to get a sense of that domain knowledge, figure out if the data is even there. Can we actually develop models that will help our clients? And if we don't do this quickly enough, the client may lose interest. Their roadmap might change. They might lose trust in us. There might be reputational repercussions. And the feature engineering portion, which is going to be the bulk of this talk, how do we access data? How do we explore that data, transform that data, evaluate the features that we come up with? If we don't do that fast enough, as many of you might know, coming up with these features and evaluating these features is a very interactive and iterative process, yes? So if you can speed up marginally even the speed at which you develop your intuition and transform one query or run one query, it has amplifying effects down the chain. So with this illustration, and we'll come back to this over and over, but what I'd hope to do is give you a very abstracted view, very high level view of where the challenges that Wasim is going to be diving deeper into come from. So in the yellow, we have the very, very different data domains I was talking about earlier. We have a warehouse, a data lake, and other sources, right? So Teradata, you might have KDB, you might have Postgres systems, SaaS servers, and data's living in all these disparate domains. In the blue, we have our research environment with our multifarious NVIDIA GPUs. And over there, on the right-hand side is a set of tools used by our machine learning researchers and engineers to do this data exploration. And then, of course, the delivery environment is isolated. So the first challenge I want to point out, what I'm referring to as the ELT challenge, is ELT standing for extract, load, transform. Because data lives in disparate sources, if you have folks, let's say 80 different researchers working across 20 different domains, working with 10 different databases, they have to figure out the idiosyncrasies of each and every database, right? And you might argue that SQL is pretty common, but you might be surprised, right, across these systems. So if what one researcher learns is not very easily generalizable, the person who comes next and does their analysis, if they're depending on these data sources directly, and feature engineering requires you to create a consolidated view of your data. So moving data, transforming it, being limited to the SLAs and the user quotas and the computational idiosyncrasies of each of these data systems, navigating this space becomes very complex, which slows us down. Speaking of which, when it comes time to do the actual exploration, as I was speaking, I alluded to this earlier, in the absence of a proper OLAP system that can store data and be armed with the computational power to transform columns at a time for financial data is largely time series data. Yeah? So a lot of times our aggregations, as Wasim will talk about later, are creating these windowed views into various lengths going back into our historic data. So if the tools that we have don't support this, it slows down our interactive exploration and therefore slows down the cycle of delivery time and jeopardizes potentially the time we have to deliver to our clients. And then just one last thing I'll say before I hand it off to Wasim is the people who collect and store data do not have the same skin in the game as people who consume the data from machine learning. They are not the ones with the machine learning expertise, right? So they're not collecting data, storing data, cataloging it, adding metadata the way a machine learning expert would expect. So there's a lot of work that happens in this process to add missing values, correct distributions, and if you don't have a way to share those derived and corrected data sets, then everyone doing this analysis will have to do that over and over again. So I hope this sets the stage for where the challenges come from, and now I'll pass it over to Wasim, who's going to dive deeper.
Okay. So one funny thing, just before, when we were on the way here, Arjun, my colleague, asked me like, where were you before Borealis? And it's funny because like I started counting the companies I worked at. That includes major data warehouse platforms like IBM and Teradata. And up to like when I started reading about ClickHouse a few years back, the idea of having an open source data warehouse, and that too with this level of performance, never crossed my mind. And when I started testing it out, it really surprised me. And then the history about how it was built ground up using C++ is really amazing to me and inspiring. So talking about the problem, the extract, transform, load problem versus the extract, load, transform problem that we were facing. I'll take you through like what the problem was that we were facing and how we solved it by building an ecosystem around ClickHouse. Now, this is an example of our data sources over here. So we have the enterprise data warehouse, we have our data lake that we query using Hive, and also missing in the picture Spark. And then we have real-time data feeds coming from enterprise data services that we basically consume as part of our machine learning pipelines. Now, if you can see in the picture, I've tried to highlight how we are pushing the transformations back onto our source system. So let's say we want to extract, one of our use cases is to improve the customer's experience in the mortgage space at RBC. And for that, we want to make sure that they get the best offers, they get the best rates, and that requires us to actually build quite complex data sets telling about the customer story, about their life cycle, and it involves using a lot of sources, and these sources all have important information distributed throughout the enterprise. So we will be running queries, aggregating data on Teradata, or using Spark queries or Hive queries, or getting data out of the real-time data sources, aggregating them, processing them at source, and then putting them as Parquet files on our storage. Once we have sourced these Parquet files onto storage, then the research pipeline starts, where the researchers would start to use that data using Jupyter notebooks pandas, or DuckDB on top of those Parquet files. And then they perform further enrichment of the data, build their training sets, and move that data to more Parquet files. And this is a very iterative process because, as most of you would know, this whole process is experimental where we extract some features, work on them, train models, evaluate those models, and then repeat if we want to enhance our logic, get more data sets. And this pattern was working out, it had a lot of problems for us. So one of the problems was the sheer amount of data being accumulated in the form of files. We have like per project around 40 terabyte of data accumulating in the form of Parquet files, CSV files, and then maintaining these files and making sure that we are following the same schema. Onboarding new people is also very difficult when you have files that they need to understand directory structures. So it really slowed down the onboarding process as well. In addition, when I talked about the iteration, let's play out a certain iteration scenario. So we store some data that is in Teradata in the form of demographics, and then we get our factual data or transactional data that is time series from the data lake, and then we consolidate it together using pandas. This required huge amounts of memory and also storage. And then during the research loop, we found out we missed a feature, or we want more, we want to change our calculation or want to change the time window. This means going back to the sources, going through the pain of extracting that data again, and then testing it again. So this made the research and MLOps experience very painful. So we just talked about all these pain points that we are having with the current platform. Oh, another important part is that the knowledge sharing, where different projects are mostly using the same overlaps of data, but in different time windows or slightly different calculations, and they're pulling data in silos. So they're not aware about other teams using different data sets, for example. Now come in the new pattern using ClickHouse. Now what we did was, as you can see, like we are consolidating all our data sources in the raw form into ClickHouse. That means we have a host of different queries in different languages: Spark, Hive Query, Teradata, Bash scripts. Now we are sourcing all those raw data into ClickHouse very easily using streaming PyArrow streams. And then the transformation, which was earlier distributed across these different platforms, is now in one place, in ClickHouse. And then the research pipeline does not have to go back to the source each time to get data for new use cases. In addition, they have all the data sources that they need in one place. So there's no dealing with a data lake connection or a data warehouse connection, or even asking for access to different systems in the bank, because we kind of brought it under one umbrella. And in addition, you can see that we have also added a dbeaver toolset here. The idea here is that this opens up the data for a lot of exploration that was not possible before. When obviously you have data sitting in different data sources, running an SQL query or running a consolidated exploration across these sources is very difficult. Some researchers, like for example, in the previous use cases, would be asking for terabytes of memory on our clusters just to run these kind of analysis. All this is solved using ClickHouse, which uses around 300 GB of memory right now. But in addition to that, we got rid of all the distributed files. There's just one metadata store on ClickHouse, and people are very happy. Just repeatedly experimenting, pulling data again and again using this improved infrastructure. So this is again Jawad's diagram now, but we are basically showing how ClickHouse is now sitting as a central part of our infrastructure. And not only that, we have kind of abstracted all those complexities about different data sources, different kind of accesses. We have abstracted that from the developers, and we have built an ecosystem around it using Daxter to orchestrate our ingestions and exports, and DBT to standardize our transformation so that this knowledge is shareable across the enterprise with different people being able to look at other teams' assets and other teams' patterns to understand some common queries, most frequently used data sets, correct way to join tables, and numerous other advantages. So just to conclude, now how did we win in this case using ClickHouse and building a data ecosystem around it? So number one priority for us was for this solution to be on-prem. RBC is very, very, very stringent about regulation, about data privacy and security. We needed something that we could manage on our premises. So ClickHouse ticked that big checkbox, which a lot of major modern platforms still do not do that. The other thing is it's open source. Borealis being Borealis, we are very agile and we like to play with and experiment with different technologies, and we use a lot of open source tools here. It supports a broad level of integration. We can natively ingest PyRO pipelines. We can natively export Parquet files, have PyRO streams coming out of ClickHouse. One of the examples that I can quote here is that I talked about improving customer experience in the mortgage space and extracting massive amounts of customer information. So this query that we ran, one example is so this transactional and demographic information over 7 years from Teradata. A typical job would take around 7 hours to process and then extract out of Teradata because it's just very difficult to export data out of Teradata. The same job, once we have data ingested in batches on ClickHouse, it takes around 10 minutes. So it's super fast, very, very smooth to work with, and then overall the developer experience has improved manifold, and all of us know about the integration aspects. So with that, Jawad, do you want to add anything to this? Okay. Okay, thank you. I'll take any questions if you want to.